Now that we've explored the different variables that kind of make up the atmosphere and weather, we're going to kind of put them all together to look at circulations. This is really where you begin to see the patterns that form over the whole globe with these circulations. So with that in mind, let's see what we can see here. So we have a rotating Earth. We know that, and that makes things difficult. Also makes things livable. With that in mind, let's take a look at if you had a non-rotating Earth. If it just stayed one direction all the time towards the sun, well, one side's going to get really hot, and especially towards the equator, and the other side's going to get very cold. So what's going to happen is you would get a big circulation. The very cold would have air sinking down towards the ground there, and the other side would have air lifting up and coming around to fill in the gaps on the other side. So you would basically have a large circulation. But we have rotating. So with that, it changes that overall pattern. And it causes there to be high and low pressure systems at different spots. Think about it. If you look at this wind flow here, winds are kind of moving out away from this area here. Well, that's high pressure building into there. Around 60 degrees north is low pressure. Near the equator, basically low pressure. So you wind up with sets of high and low pressure along the world. And guess what? They actually work. When you look at the atmospheric maps and just kind of get a feel for them, notice this would be January. This is our winter. There's a pretty strong low here over Greenland. There's another one coming across Alaska. Another one out here north of Siberia. Right around 60 degrees north, you have low pressure. 30 degrees north, or a little bit right in that general area, you have high pressure. Then down southern equator, you get the same, just reversed pattern. If you move into January, what happens is the patterns, in July, the pattern's weaker in the northern hemisphere, stronger in the southern hemisphere, and you wind up maybe pushing those highs a little further north, lows a little bit further north, so you wind up with a different type of pattern. So with that, there are a polar vortex that sits over top the globe, in both the North Pole and the South Pole. It's planetary scale, mid to high latitude circulation, and it actually has an influence on our weather. You may have heard about the polar vortex or Arctic or Antarctic oscillation, but what they basically are is just a very strong upper level low pressure sitting over top the poles. And when that pressure system weakens, what happens is instead of the winds just flotating around it in a complete circle, they begin to buckle. And what happens is that allows some of the Arctic air to come south. So that's where you get the polar vortex and all. The stronger it is, the more the very cold air is kept to the north, the weaker it is. It allows more of that cold air south into the United States, for example. In the mid-latitudes where we live, we have an oscillating wave pattern, highs, lows, and it doesn't look nice and pretty like this one maybe, but it is similar always. There's always a series of waves around the globe. Now, the tropopause, we know, we've learned, and it's been hammered into you, that the colder the air is, the lower the tropopause is going to be, the warmer the air is, the higher the tropopause is going to be. Near the pole, the tropopause is fairly close, always very much lower. In the down over the equator, yes, it's much higher. However, in between, where we live, it kind of fluctuates. And it fluctuates depending on cold fronts and warm fronts that move through and low pressure systems that accompany them. So your mid-latitude tropopause can be variable. Over the trade winds, trade wind inversion we're talking about here. There's a descending branch of the southern Hadley cell right over the middle of that high pressure area that we have there. This kind of stabilizes some of the air in the lower to mid levels of the atmosphere. So it keeps along the trade wind some less clouds, less precipitation. And with that, here is the intertropical convergence zone. That's basically where the southern hemisphere's winds meet the northern hemisphere's winds. The real key I want you to notice here is that right over the oceans, they're not moving a whole lot. Why is that? Because the oceans take a lot of heating, a lot of the sun's energy to heat up. So that temperature change, while it does occur, is not nearly as great as it would be over land. So notice, over land, the intertropical convergence zone moves much further north in the summertime, or in the wintertime, it moves further south. So this is something that is very important when we get to monsoons. And here's the monsoon that goes with that. Think about it. The intertropical convergence zone moves north. What happens? Winds come out of the south. All of a sudden, all that moisture in the Indian Ocean, Bay of Bengal and all, starts hitting into that area. Lots of rain during the summertime. Wet season. Wintertime, what happens is that intertropical convergence zone moves back south, and you wind up with very dry weather. There's also something interesting on these high pressure systems at 30 degrees north. Think about it. If you live on the East Coast, the high winds are flowing clockwise. So where are they coming from on the west side of the high? On the west side of the high, they kind of come out of the south. So if they're coming out of the south, they're pulling moisture up from the tropics. And we wind up with a more humid, more unstable, more precipitation, which what happens at Charleston, South Carolina. Charleston, South Carolina and San Diego are very close to the same latitude. San Diego, on the other hand, has this big high sitting out to its east, actually it's west, excuse me, and it will pull down winds from the north, dry winds, and they wind up with a distinct dry season in the summertime when it's mainly being influenced by that high. These highs are so long-term that they actually have caused the oceans to begin to move with the highs. We talk about the Gulf Stream over here, coming up along the East Coast, which keeps the East Coast of the United States a little warmer than it would be. It also influences some of the Iceland and that area up in here, that whole Gulf Stream. Well, look at this. There's a North Atlantic gyre. Where is that? Over top of that gyre sits the subtropical high pressure system. That's been sitting there flowing clockwise forever, and the oceans have responded. Now they flow in the same clockwise manner. There are monsoons that occur in the United States as well. We have the North America monsoon. This happened to be a lousy year for that if you were in Arizona and New Mexico. They didn't get a lot of rain at all. Matter of fact, Phoenix, Arizona had the lowest rainfall total in the last 150 years from this year's monsoon. Generally, they get about 75% of their rain in the monsoon season in the summer. So with the fact that they've had hardly any, like less than a half inch over the summer, means they're in for possibly a very, very dry and harsh winter. Drought may be a very prevalent thing out in the Southwest this year. What happens to cause this monsoon is there's a mountain range, actually right along the northwest part of Mexico here. And with that mountain range, you wind up with heating that actually occurs aloft. Heating causes there to be a low pressure develop at the surface there, but aloft, remember, the temperature goes, because it's very warm, you actually wind up with high pressure. So you wind up with high pressure that forms over that area. Now that you have the high pressure and low in place, low is counterclockwise circulation. Well, notice that pulls in air from the Gulf of Mexico and from the Pacific into that area. You wind up with lots of thunderstorm potential in that area during the summertime with this. Rossby waves. They are, when you look at waves in the global picture, let's see if we can look at one a second here. So I wanted to show you a Rossby wave, and it's not exactly the easiest to see all the time, but let's take a look at one and see if we can spot one today. All right, here is a picture of the 300 millibar jets. We talk about the wave pattern, and notice, winds go down here, they come up here, they go down here, they come out here. You would argue there's probably some kind of a low pressure area over this area, Siberia. There's another one, and it's hard to tell if there's one here in the central United States at this time or the eastern United States. But there definitely is a ridge of high pressure here over the Atlantic Ocean. So I would argue that this low probably into this area somewhere. These broad waves, this one here, and over in this area, one over here, are called Rossby waves. There are little tiny features like this little low will be rippling through this Rossby wave. Or these probably have this low here, this low here. They're shorter wavelengths, and they move through the big pattern. When they come into the Rossby waves, they tend to intensify. When they move out, they tend to weaken. So that's one of the things what meteorologists look for, these long waves, to see where these little impulses of energy are going to have the most impact. And we could also look at this and just take a look at global circulation again. We've just been talking about that. And here is our global circulation today. Well, golly, there's the high pressure. High pressure over here, a couple of tropical systems in here. Oh yeah, look where the low pressures are, up around 60 degrees north around the globe. High pressure over the pole, and the intertropical convergence zones down in this area. So we're seeing the pattern. Maybe a lot of little nuances that aren't quite the same, but we are definitely seeing the pattern. So let's keep now. If we get this in, we get what's called zonal flow and meridional flow. If you remember, over the Pacific, we had a pretty much west to east, pretty long, straight wind field. That is a zonal flow pattern. However, over the United States, we have it buckled up and down, more intense from the north to the south. They're meridional. Meridional will have much more temperature extremes than the zonal flow. Both can have weak low pressure systems along them. Meridional's lows will tend to be stronger because they're more intense systems and they have more cold and warm air contrast. However, you can get fast-moving low-pressure systems in zonal flow as well. But zonal flow, if it goes across the United States, tends to keep the northern United States quite cool. Southern United States, not too bad. Pretty nice place to be at that time. Sometimes you get blocking patterns, and we kind of have one right now that's sitting over the eastern United States, where we got that cold low sitting there, and to the east you saw high pressure. They kind of form at some times of the year, and when they last, they can linger for 2-3 weeks sometimes. And they're not fun, depending on which side you're on. If you're on the nice sunny side, that could be very pleasant. If you're on the rainy, cold side or snowy side, maybe that's not so good. And here you can see an example of one that occurred, blocking pattern that just kept sitting there. And the Midwest got clobbered with rain in 1993 and gave some record floods on the Mississippi River. And you can see how much rain fell there. So the polar front, very narrow transition zone between cold and warm air masses. Cold air we know is denser than warm air, so the pressure drops more rapidly. So you create a pressure gradient across there. This pressure gradient tends to be strongest near the tropopause. So that's why our jets are up higher. Coriolis effect does balance it, and jet streaks develop where the polar front is well defined. In other words, the stronger the temperature contrast, the stronger the jets will be. There is a seasonal shift to that front. And that's where we're going through a transition right now from the summer season to the winter season. So the jets will be getting to move further and further south across the United States during the next several months. And right during the summertime, summer jet pretty much comes across the north. Almost no jet in the southern part, very light winds. Wintertime, it begins to deepen, more possible in the southern part. All right, we're going to learn a little bit about how low pressure systems. We've talked about divergence and how divergence aloft can allow waves, air to come into that area and move up. Well, with a jet, there are a couple things that are going on in a jet. One, you have very strong divergence in the left front area. So what happens is you wind up air rising. That tends to form a low. A low, you think about it, the air is coming together. That's pulling a warm, increasing the temperature contrast. So you wind up with low pressure developing under that area. By the opposite, on the back side, you have sinking motion and you have high pressure. So when you see these troughs in the sky, which you don't see, of course, if you had them analyzed for you, you would wind up seeing ahead of it low pressure, behind it high pressure. And here you can see that jet and divergence in the left front and the right rear, convergence in the left rear and right front. Knowing where they are at that way, that typically occurs, you can actually combine jets to get stronger divergence sometimes. Another feature that is part of the planetary circulation is El Nino and La Nina. We're going into an El Nino right now. And from a historical perspective, they kind of occur every 2 to 3 years. The Ekman spiral occurs along the ocean. It's governed by the Coriolis effect again. What happens is, say you have steady southerly winds or southwest winds right along the Atlantic coast. I'm going to use Cape Hatteras as a perfect example of this because they get a lot of this. When that wind begins to move the water to the north there, the water wants to shift to the right. Its Coriolis effect begins to take effect. And the longer this duration occurs, the more that water flow is going to turn to the right. While it turns to the right, it's turning away from the coast. When it turns away from the coast, what do you get? You get the bottom water coming up. So you wind up getting temperatures going from 80 to 85 degrees or whatever one day on the ocean to 60 degrees the next. And it has happened along Ocean City, along Hatteras and all that area there. And there are different phases of El Nino we're going to talk about a little bit here. Not much. I want to show you a map here. Kind of gives a really good example of El Nino, what's going on here. Currently, we do have an El Nino, and this is the temperature curve. We pick an area in the Pacific where we take how much above normal the temperature is. Here is how that temperature curve is tracked. We have been having a La Nina for the last several years. Well, look at it. Here's the La Nina threshold. Here's El Nino threshold. El Ninos can be really, really intense, and this one seems like it's trying to be one of those. And the more they're intense, the more they influence our atmosphere and our weather. So how do they do that? Well, let's take a look. Here is the actual temperature difference, and you can see very warm conditions off the out in the Pacific here, well above normal. Let's go up here to look. Here's the areas the El Nino influences, it impacts. What it does is cause pretty dry weather up in this area, wet and cool down in the southern United States. If you're back over areas in Australia and all that, you're going into a drought with possible with this kind of conditions now, warm and dry. So you can see El Nino impacts all kind of stuff over the world right now. And interestingly, our El Nino, if it's very, very strong, can pull in tons and tons of atmospheric rivers into the west coast of the United States. And because it's further south, it's going to have more moisture to work with. The potential is always there for heavier snowstorms, assuming it gets cold enough. I have seen El Ninos where it actually can never get any Arctic air or any Canadian air even hardly into the United States. And we wind up staying mild all winter, but maybe with a lot of rain. And sometimes there are other years where the exact opposite happens in the sense of cold air does seep in, and we wind up with tremendous snowfalls instead. So it'll be interesting to see how this plays out this year. I hope you got a little bit out of this, and let me know if you have any questions.